we have Stavros Katsanevas, and he's going to talk to us about gravitational wave detection at the moon, continuing the theme, in particular the project of a lunar seismic and gravitational antenna.
Yes, first of all, thanks to Joris for a very nice introduction on the subject, which will save me some time. And then, of course, the team is made by myself. I'm director of European Gravitational Observatory, which is the home of the Virgo antenna, as was mentioned by Joris. And then Kopiais Lenuné from IPGP, well known among the fathers of the InSight seismometer, and Simone Dell'Agnello, who will be talking afterwards. And the collaboration is, of course, international: France, Italy, UK, Germany, Israel, Greece, Poland, and US. Next slide, please. Now, what we try to do here is exactly to combine two ideas: the idea of understanding better the lunar interior structure, surface and subsurface from the, let's say, the geoscientific point of view, because it is coupled to how we will be detecting gravitational waves and gravity in general, and also probably ultra-high energy cosmic rays. So it's three instruments: an optical very broadband seismometer, a lunar surface laser retroreflector, and a fiber-distributed acoustic sensor, more or less the same as what you will hear in this next talk. So next slide, please. And what I'm presenting is a pathfinder to a 10 by 10 kilometer L detector. Now, the first instrument, the optical very broadband beam, is of course inheritance of the Farsight seismic suite, which is a mission selected by NASA already in 2024, which will be more or less a little bit better than the InSight. It will be with an acceleration sensitivity of 10 to the minus 10 meters over second square, and will make through this, this determination of the lunar interior structure, near side versus far side. Is it tidal effects, or there are earthquake and moonquakes all over the place? Thickness of the crust, composition of the mantle, etc., etc. Understand better the moon, and more or less its sensitivity is around the decihertz to hertz level. Next slide, please. It is what it is very interesting in it. It is an optical, and it has a three axis inertial sensing, and we'll use a lot of knowledge. We'll shield it from sun radiation. We'll have feet on the Earth, on the Moon. I'm sorry, to penetrate the regolith for better stability. And it's not very heavy, 20 kilograms, data rate 1 gigabit per day. It is already something that is funded by the European Union, and together with CNES, the Space Agency of France, there is a program till 24-25 to have a TRL of 6. And this will get performances below 10 to the minus 11 meter per square of second, between 10 millihertz and 1 hertz. Next slide, please. Something that most of you will know, but I would like to repeat things that were already said by Joris, your essential seismic environment, which is also, of course, background to the gravitational waves, is the deep moonquakes, which have long codas. They are coherent. It's like global events. They are of the order of 1/10 of Apollo DU, but they are similar in waveform when coming from a given fault. Therefore, you can, by identifying well the waveform, you can have a resolution better by, let's say, 1/10 of what is your instrument resolution. The other things that can hurt you is the meteoroid impacts. There it's a shallow surface scattering, our long codas, but longer wavelengths. Therefore, as we will propose a 3 kilometer, we will have multiple sensors around the 3 kilometers, as you will see, through a fiber. And this would permit us, by localizing, to again have a handle to control seismic environment. Last but not least, as also was said by Joris, it's the Lunar Background Hum, a continuous hum, which can go down to the picometer or half a picometer or even less level of sensitivity. And this is where, again, we hope that the fact that we'll have multiple sensors we would have some handle on controlling. Next slide, please. Then the second instrument is the lunar surface laser retroreflector. Again, here I will profit from the fact that we'll hear about it in half an hour. We profit from the heritage of moonlight, where it has a few very important innovations, 10 centimeters cube corner reflector, precise pointing, dust covers, and things like that. Very interesting gravitational potential, but also gravitational wave potential, already by the lunar ranging with the Earth. But what we propose is to have, next slide, essentially create a lunar laser strain meter of 3 kilometers. So we'll have the laser on one side and 3 kilometers further down the retroreflector. And you would, if you make the standard calculations of what power remains after you calculate reflectivity, efficiencies, lunar dust, and things like that, with the new technologies, you have the shot noise level, which can give you a relative strain, if you remember a little bit, but I will come back to that when I start comparing everybody, of 10 to the minus 19th, which is an extraordinary, very good sensitivity on relative strain. And but of course, there again, this is only the intrinsic, let's say, sensitivity. And you have to take into account, one of the things you have to take into account is, for instance, lunar hum, which would be 10, in this distance, it would be 10 to the minus 15, 10 to the minus 16. But you can find ways to protect yourself through the, tripods and things like that inserted into the moon. Let's go further down. Next slide. Then, last but not least, is an engineered fiber distributed acoustic sensor where you shoot a laser and you get the backscattered Rayleigh light. And this through optical domain phase comparison, you can have essentially, you can measure disturbances all along the path according to some gauge length and time length. And so you have a multi-sensor, a stacking in space and time possible, and eventually source localization. And with this, depending on the process of reflection that you use, you can measure strain, acoustic signals, and temperature. Next slide, please. Next slide. So the sensitivities that have been obtained with this engineering FDAS are quite good. For instance, if you have a gauge of 30 meters, you have a good, and you deploy the fiber, of course, on the moon surface. You can have 100 sensor points, each one with some relative sensitivity of 10 to the minus 13. And if you divide by the square root of 100, you get 10 to the minus 14. And if you are very ambitious, you could get down to, let's say, 10 to the minus 14, to 10 times 10 to the minus 15 by more powerful lasers, increasing the pulse width, and also increasing the gauge length you're measuring. Of course, there is a thermodynamical limit, which is theoretical, not measured. It's one of the goals of our collaboration, is that on 1 millihertz, which is 10 to the minus 15, it would be probably very difficult to go below 10 to the minus 15 over square root of hertz. Let's go next slide. Now, let's come to the gravitational waves. We form a sort of group of three. There are three proposals. You've heard the previous one by Joris, Jan Harms, and others. Ours, you just heard a few elements. And there is a US proposal essentially to reproduce LIGO and Virgo at the moon. And we made a very interesting, with a lot of participation, a workshop here in IGO, in the Pisa in October 2021. We are, as it was also mentioned by Joris, funded by EC for Organization of International Fora, etc., etc. And we participate, of course, the ESA Astronomy and Geoscience topical teams. Next slide. Why go to the moon? it was said more or less that you cover between the millihertz and the hertz region, where you detect essentially the intermediate band black holes, where they are between the stellar black holes and the black holes that are the center of the galaxies, let's say. And so you can see their formation. You can serve, it was also said by Joris, you can have low latency alerts and also multi-band analysis, which is a very important thing. If you measure both the inspiral and the merger, then you get a much better handle of the parameters of the objects that merge. You can have access to double white dwarfs as progenitors of supernova 1A. It has not yet been solved. Core collapse supernova, etc., etc. And of course, stochastic backgrounds of cosmological origin. And above all, another thing that is very interesting, you have a longer baseline, either with the Earth or let's say parallax type, as the moon goes around the Earth. If you have inspiraling above 1 month, you can use the position of your data to have a much better pointing accuracy. Next slide. So, how do we detect lunar vibrations? It's an old story. This is how it started by Weber. It was very well presented by Joris, so I will not say much about it. You have one possibility here. It's the model by Jan and others, Jan Harms and others. You have, as we said, you just take the normal modes of the moon, and then you either assume a very optimistic flat rate after the 10 millihertz, or actually not rate even, it's a multiplication factor, the multiplication factor that you get from the moon, or it goes down, and it is actually what you've seen in Joris' presentation. It had this fall down at the higher frequencies. We had made with Josef Mastorovich, that had made a long time ago some analysis on Earth, the same simulations to the moon, and you see that, as we said already, up to 10 millihertz, you get multiplication factors of the order of 10 to the 6 and above, 10 to the 7, and even if you are very optimistic, 10 to the 8. And of course, as you go towards the hertz region, you lose 2 to 3 orders of magnitude. So where you will get, yes, next slide. Next slide, please. So very fast, the sensitivities you can obtain, assuming an optimistic 10 to the 6 factor, and otherwise, in more realistic scenarios, by introducing these simulations that I just said, to 10 to the minus 13 or the optimal 10 to the minus 14, this is how you compare, for instance, to LISA, which is the blue line, we are the red one, and also the Earth detectors. Next slide. And again, the argument that this gives you access to the intermediate masses, and furthermore, it gives you to the continuous inspiraling phase access, so that you can have a low latency alert for the Earth detectors. So these are the biggest advantages that you can have. Next slide. You have a series, I mean, this is, since we don't have much time, I told you that you can have optimal angular resolution because of the biggest baseline. Let's go further down because I want to go to the deployment issues. Next slide. Merger scenario, the same that Joris has shown. You can have what I said, you can have days to months to years of low latency alerts for the other observatories on Earth and also the standard observatories. One more slide, which is you can have access to the formation of intermediate mass black holes, and also even the stochastic gravitational wave background, all the things that come from cosmology, or the link, if you want, to particle physics type of physics, leptogenesis, phase transitions, first order phase transitions, etc., etc. Next slide, please.
Okay, we need to finish up.
Yeah, sure, it goes very fast. Yep. Another thing I don't have time to go is, as I said, it is also an acoustic detector, because you can tune it to have acoustic detection. And there you might use it, since you don't have an atmosphere, your cosmic rays, very high energy cosmic rays, have an impact on the lunar surface and they produce a sound. And you can detect that. It is an old idea, and again, by Volovic and Christiansen. And we have made simulations that were very optimistic. We are not yet sure, because we have to, some of the parameters are not well defined, hopefully better defined in the next 2 to 3 years, that we could have detecting areas similar to what you have in the bigger ultra high energy cosmic ray detectors on Earth. Next slide. These approaches are complementary because the optical, the OVBB is optimal in the 0.1 to 1 hertz bandwidth, and so for seismological regions, but also serving as calibration. The FDAS, as I tried to say, it can measure lunar seismic hum, individual impacts and things like that in practically all the frequencies, and both the reflector and the FDAS can have optimal response in the 1 to 10 millihertz range, where they profit from the multiplication factor of the normal modes. Next slide, and it's my next to last. Deployment issues. You have to deploy.
Can you please make it quick?
Yes, it will be very quick. You have to deploy it in 2 different sites, of course, that are different by 3 kilometers. So you have 4 pallets, and we hope to use a hopper or a deployment rover, but we tend more to use a hopper, as it, for instance, you have by Martin et al. In the Lunar and Planetary Science Conference 2022. And we believe that this is essentially the biggest risk of our experiment. Other issues, power consumption, data rates, radiation protection, and thermal issues, especially the thermal issues, we'll study them through at the Negev Desert, and we have the full ESA, Israeli Space Agency, support for that. And I will leave my last slide, which has for your perusal, and get any questions if there are.